Hi, everybody. We're going to take a quick look here at activity 8 on triple integrals. And if you haven't done it yet, I would suggest that you close this video and work on it yourself because you're going to learn best if you have tackled it, at least initially, gotten as far as you can, and then you're coming to this just to make sure that things are the way that they should be. Um, Okay, first problem is find the volume of a sphere with radius 1 using a triple integral and cylindrical coordinates. Um, so, first off, we have our sphere with radius 1 here, x squared plus y squared plus z squared equals 1. No big deal. And if we're changing this into cylindrical coordinates, it means that we're using polar coordinates in the xy plane and dz for the z component. Meaning that if we solve this for z, we're going to get an equation for the upper half hemisphere of the sphere when we take the square root of this equation. So z equals the square root of 1 minus x squared plus y squared is going to be a good equation for that top half bound because we're changing it in the polar and the xy plane. X becomes our cosine theta, y becomes our sine theta. Our volume differential becomes r dz dr d theta, and then probably this will be pretty smooth sailing for the rest of the thing. For this one, I've chosen to use a bit of symmetry since we're just finding the volume here, and the integrand would be very plain and symmetric with respect to z values and r values and theta values. We can exploit some of the symmetry, and instead of going from negative square root of 1 minus r squared to positive square root of 1 minus r squared, I'm going to say 2 and just go from 0 to the top part so that we're just integrating over the top portion of the hemisphere, but we're multiplying by 2 so that we get the volume of the entire sphere. 0 to 1 on the radius because we're working with the sphere of radius 1, and the shadow of that sphere in the xy plane would be a unit circle. And again, since it's a unit circle, theta is going to go from 0 to 2 pi. Once you have that done, integration's roughly straightforward. I do think a u sub at this point is a good move. So we've got a little u equals 1 minus r squared there. And yeah, pretty smooth sailing from there on out. And we get the desired value of 4/3 pi. Yeah. The volume of a sphere in general is 4/3 pi r cubed. So since the radius of this sphere is 1, we're expecting 4/3 pi as an answer. Okay, let's see how that compares with the volume of that same sphere using a triple integral and spherical coordinates. Cool. So same equation. A way to write this equation in spherical coordinates is just that rho equals 1 because rho is equal to x squared plus y squared plus z squared. This is the radius of the sphere. And yeah, since we're integrating over sphere, all of our bounds are going to be nice constants. The radius of our sphere is going from 0 to 1. The phi angle from the positive z-axis down to the negative z-axis is going to go all the way from 0 up top down to pi on bottom. We want to sweep out all of that angle. And then theta in the xy plane is going to sweep from 0 to 2 pi. And we've got rho sine phi d rho d phi d theta as our volume differential. And so, yeah, this is Who would have thunk that integrating over a sphere would be a place where spherical coordinates shine? Um, Still, integration's not, completely simple, but it's not too bad. And eventually we get to 4/3 pi again. Um, yeah, this is, these are what I would say fairly test level questions. Um, Notice that, yeah, I'm asking you to convert something that's, I don't know, not too complicated to translate into cylindrical or spherical coordinates. Um, Notice that the integration, while this one does use a U substitution, the integration's not too bad. You're not having to use trigonometric integration where you're subbing in double angle formulas and stuff. Um, yeah, so I like these questions, and things that show up in your test might be similar to this. Um, cool. Last one, a big one. Um, okay, that's actually something that I can click later. Dude, the scroll wheel on this mouse is nuts. Okay, we have our region, and we are saddened by the fact that if we were going to integrate over this region in rectangular coordinates, we would need to set up three integrals. Because let's just say we're going dy dx. If we're going dy dx, then blue would be our top. We would be, integrating from somewhere over here, like, I don't know, negative 1.75. And starting there, our top function would be blue, our bottom function would be red. We'd be integrating. Oh, then we get to here, and our bottom function would be green, and our top function would be blue. So that's a different integral, and we'd be integrating. We get to here, and now our top function needs to be orange, and our bottom function's green. So that's a third integral, and we'd integrate and be done. I mean, there's an argument to be made that maybe three integrals that seem more familiar might be easier to do than learning this whole new thing of, um, you know, substitution and changing uh, variables. But yeah, we're going to do it. It's going to be great. Um, the first thing that we need to do is write the equation of each boundary so that the constant's on one side. That helps us identify which substitution we're going to make in, because the substitution hasn't been specified in this problem. But once you solve for a constant number on the right-hand side, we're left with y minus 3 halves x and y minus 3 halves x in two of the equations, and y plus 1/4 x in two of the equations, which gives us the hint that if we set u as equal to y minus 3 halves x and v as y plus 1/4 x, then our boundaries are going to be a bunch of constants, which will be great. And we'll be integrating over a rectangular region rather than this awkward parallelogram. Okay. So that gives us the substitution that we're going to do. So we're looking to change this whole thing into u and v coordinates instead of x and y coordinates. And in order to do that properly, we find the Jacobian determinant, and finding the Jacobian determinant requires us to solve the system of equations that we have here in purple for x and y so that we can take the appropriate partial derivatives here. So remember, we can use substitution or elimination to get these equations that are solved for u and v into equations that are solved for x and y. Um, but I think elimination seems to make a lot of sense. For instance, if we subtract the second equation from the first equation, we get u minus v, boom. We get y minus y, 0, and negative 3 halves minus 1/4, negative 7/4 x. We eliminate that variable y right off the bat, and we're able to solve for x fairly easily. When solving for y, you'd want to make sure that the x's cancel. So we'd be multiplying this whole equation by 6, and then adding the two equations together gives us this over here. And once we solve for x and y, we're able to, yeah, do this Jacobian determinant and translate from xy coordinates into uv coordinates. So yeah, remember that the gradient of x with respect to u and v is in the top row. The gradient of y with respect to u and v is in the bottom row. Taking those partial derivatives from this equation is not so bad. We get to this part where the actual determinant would be a negative 28 over 49. But remember, in this case, we're just looking for a positive scale factor between the two coordinate systems. And so we take the absolute value of that and get 4/7. And then I think mostly the hard part of this problem is done. The rest of it will be just, translating it back into an integral and then solving the integral. I guess the integral takes a number of steps down here. But we have our scale factor. So 4/7 dv du makes sense as an area differential. To get the bounds on our integral, we're going back up to these equations and seeing, oh yeah, we define this so that v would go from 1 to 4 and u would go from 2 to 4. So that part's looking nice. And then going back to the original integrand, we didn't really optimize things to make the integrand nice in this time. We were looking to make the bounds easier. And so the integrand's going to look a little yucky, but we're just, subbing in for 2 times x. X is negative 4/7 u minus v. Wait a second. That's 2y. Good grief. Okay. 2y. This is y. That's why that's there. X is this one. That's why that's there. And then, simplifying. The integrand doesn't look so bad once you simplify things a bit. You can even get it to look really nice by taking out this factor of 80 or 8 over 49. But then, you're just integrating all the way down. And the number that you would get in the end is 816 over 49. Real quick, I don't know that this is going to help a ton at this point, but we have our bounds there in slanty stuff. So this is in XY coordinates. This is in UV coordinates. And I don't know, this is a view with both of them at the same time, which kind of gives you a perspective on each of their areas. So what we had found when doing the Jacobian is that This smaller area is 4/7 of the larger area. So if you multiply 4/7 times this area in UV, you get back to the original area in XY. Cool. Anyways, yeah, if you have any questions that are left on the activity, please let me know. Um, Otherwise, I'm going to work on the homework and make sure to get you a video about that soon. All right, have a good day. Bye.